Today we're going to evaluate a nice integral. So the integral in question is the integral from 0 to infinity of x to the 5 over x to the 6 plus 1 times the hyperbolic sign evaluated at pi x. Now we're going to use two tools that we developed in previous videos and then prove one new identity that we'll use. And so these tools involve interesting series for the hyperbolic secant and the hyperbolic cosecant. And well, here are those series in question. And if you want to look up the name of the videos where these come from, they are Amazing Techniques for Uncovering This Series and A Surprisingly Nice Integral. Now, the other tool or identity that we'll make use of is this integral of x to the 4th over x to the 6 plus 1 from 0 to infinity. So we'll show that that's the same thing as the integral from 0 to infinity of 1 over x to the 6 plus 1, and thus they're both equal to, well, pi over 3. Okay, so let's start with this integral from 0 to infinity of x to the 4th over x to the 6 plus 1. And let's start with the substitution. So let's set x equal to 1 over u, but let's observe that that's going to make dx equal to minus 1 over u squared du, just from taking the derivative. Okay, well, what about the bounds of integration? Well, let's notice as x goes to 0 from above, that means u is going to positive infinity. Just keep in mind that if x is 1 over u, then u is also 1 over x. And then as x goes to positive infinity, which this is positive infinity, u will go to 0. Okay, so let's see what we have here. So that's going to leave us with the integral from infinity to 0 of 1 over u to the 4th all over 1 over u to the 6 plus 1 times minus du over u squared. Okay, so let's see if we can do something to that. Well, let's observe that we can multiply the numerator and the denominator by u to the 4th. And in the numerator, that's going to leave us with simply 1. And in the denominator, that's going to leave us with u to the 6 plus 1. That's because the u to the 4th is going to build up with this u squared that we get from the du component to give us u to the 6. That'll multiply into this thing that's already in the denominator to give us u to the 6 plus 1. Now I'm going to take this minus sign and have it change the order of the bounds of integration to 0 to infinity, and then that'll be du. But now I'm just going to do a change of dummy variables back to x. We have the integral from 0 to infinity of 1 over x to the 6 plus 1 dx. Okay, so we've proved that these two integrals are the same. Now let's show that they're equal to pi over 3. And the first step of doing that will be to start with this integral from 0 to infinity of x to the 4th over x to the 6 plus 1 and write it as 1/2 of itself plus itself. So I'm just going to write that down, x to the 4th over x to the 6 plus 1 plus 1/2 of the same thing. But then I'm going to use this equality to write the second version as simply 1 over x to the 6 plus 1. But now I can push these two things together to give me 1/2, and then I have my integral from 0 to infinity of x to the 4th plus 1 over x to the 6 plus 1 dx. So I've got something that looks like that. Now, well, where are we going to go from there? Well, now I'm going to add the number 0 to this in a really clever way. And simultaneously, I'm going to factor that x to the 6 minus 1 using a sum of cubes formula. So let's see, that's going to give me 1/2, and then I have the integral from 0 to infinity of something over. Now let's factor this as x squared plus 1, and then x to the 4th minus x squared plus 1. And that in the denominator is our sum of cubes formula, where we're thinking about that x to the 6 as x squared cubed. But that gives me motivation for what I want to do to that numerator. I'll take that numerator and I'll write it as x to the 4th minus x squared plus 1, and then plus x squared. So let's observe that I subtracted x squared and then I added x squared. But I did that because now I can see this as grouped x to the fourth minus x squared plus 1. And then this x squared is kind of by itself. So the orange grouping will cancel what's going on in the denominator, this x to the fourth minus x squared plus 1. And then this green parentheses thing, well, that's just going to live on top of our original denominator because I'll push that back together. So what I mean here is I have the integral from 0 to infinity of, now this is going to be 1 over x squared plus 1 dx. So that's from my orange stuff. And then I'll have plus a half integral from 0 to infinity of x squared over x to the 6 plus 1 dx. So I'm left with something like that. Okay, great. But now what I want to do is go over here to this peach underlined integral and do a change of variables. And the change of variables will be to set u equal to x cubed. But observe, that means that du is equal to 3x squared dx. But that means that x squared dx is 1 over 3 du. So that'll change my entire integral from the x world to the u world. So let's see what that looks like. I'm going to bring down the first, so I have half integral from 0 to infinity of 1 over x squared plus 1 dx, and then plus, so I've got a half and then a third, so that's going to leave me with a sixth, and then the integral from 0 to infinity. My bounds of integration don't change here, kind of for obvious reasons. And then I have 1 over u squared plus 1 du. And that's because this x squared dx gets gobbled into this 1/3 du, and then the x to the 6, well, that's clearly u squared because it's x cubed squared. But now what I can do is, well, think about this number half as 3 over 6. And then I can push these two things together. So 3 over 6 plus 1 over 6 is 4 over 6, which is 2/3. And then I have the integral from 0 to infinity of 1 over x squared plus 1, where what I did is I just changed this back to x variables because that's just a dummy variable. But now I can, well, we might know the value of this integral already, but let's just do all of the steps here. So this is going to be 2/3, and then the limit as x goes to infinity of the inverse tangent of x minus the inverse tangent arctan of 0. So that's taking the antiderivative, plugging in the lower bound, and then taking the limit as the upper bound approaches infinity or grows without bound. So I think we probably all know that the inverse tangent of 0 is 0. That's because the tangent of 0 is 0. And then as the argument approaches infinity, the inverse tangent approaches pi over 2. So that gives us 2/3 times pi over 2. In other words, that gives us pi over 3. But let's see, that's exactly what we wanted. We started over here at this left-hand side and ended up with pi over 3, meaning that we've got this integral right here is equal to pi over 3, but then these two integrals are the same, so they're both equal to pi over 3. Okay, so that's good. So we've actually got one more tool that we need to derive, but I didn't really have a space for it right here on the board. So let's do that on its own, and then we'll just keep it in mind as we do our final calculation. Okay, so the other little tool that we need, which is really can be seen as a little part of our final calculation, as you'll see, this makes our final calculation really quick, but it's just nice to see it kind of on its own, is, well, this integral from 0 to infinity of x to the 6 over x squared plus n squared times x to the 6 plus 1. Okay, so we're going to start here by adding 0 again, and we're going to add 0 in a way that will cancel out this x squared plus n squared. So it's going to look like this. We're going to have the integral from 0 to infinity, and then my numerator is going to look like x to the 4th times x squared plus n squared. And then I have to subtract n squared times x to the 4th. And so as you see, this will cancel out with this x squared plus n squared in the denominator. So that was like our whole goal there. So let's maybe look at these one piece at a time just so that we're clear. So let's take these orange parentheses. So for that stuff in the orange parentheses, the x squared plus n squared will cancel, leaving us with our familiar x to the fourth plus, or x to the fourth over x squared plus 1. And then let's see, for the other bit, we'll have minus n squared and then the integral from 0 to infinity of, and now notice here the denominator doesn't cancel at all, so I'll just write my entire denominator there. And then another thing that I want to do is factor out this minus sign, so we're really factoring out a minus x squared. That leaves me with an x to the fourth. But I put it way over here on the left of my numerator because I'm going to add 0 again. I'm going to subtract into the fourth, and I'm going to add into the fourth as well. Okay, so I think that looks good. But now let's look at these things in red parentheses right here and observe that I can pretty clearly factor this as x squared plus n squared times x squared minus n squared. And so that'll be how I split this thing up. I'll let that first one cancel with the x squared plus n squared in the denominator, and I'm going to be left with an x squared minus n squared in the numerator. Okay, so let's see what that gives me. So as you might recall from our calculation over here, this first integral is pi over 3, and then I'll have minus n squared, the integral from 0 to infinity of x squared minus n squared over x to the 6 plus 1 dx. So that's again from canceling that x squared plus n squared in the numerator and the denominator from those red parentheses. And then we'll have minus n to the 6th, and then the integral from 0 to infinity of, well, we've got this whole denominator now, x squared plus n squared, x to the 6th plus 1 dx. But now I'm just going to insert the value of this green overlined integral. Some of that is stuff we've already calculated. The n squared over x to the 6th plus 1, well, observe that that's just exactly related to this 1 over x to the 6th plus 1 from our previous calculation. And then the x squared over x to the 6th plus 1, we actually calculated essentially that same integral using substitution from before when we were building this new tool here. So I'll just put a star that both of the pieces involved in this green overlined integral, after splitting it up per the numerator, are taken care of from previous calculation. So that's going to leave us with pi over 3. And then we'll have minus n squared times pi over 6, and then plus n to the 4th over 3 times pi. So we've got something that looks like that. And then from here, for this second integral, I'm going to go up here to this 1 and replace it with x to the 6th plus 1 minus x to the 6th. Again, that's just adding 0. And then I'm going to take that and, well, split it into two integrals across this thing where I'm grouping that in green parentheses. So let's see, that's going to give me a minus n to the 6th. I have my integral from 0 up to infinity of 1 over x squared plus n squared. That's from my green parentheses. And then for my other term, I have plus n to the 6th, the integral from 0 to infinity of x to the 6th over x squared plus n squared, and then x to the 6th plus 1 dx. Okay, so we've got a lot of moving parts here, but now we're left with something like this. But now what I'd like to observe is this stuff way over here that I've generated on the left-hand side is exactly equal to the stuff that I started over here on the right-hand side. I just got my left and right mixed up. The stuff that I started with on the left hand is what I ended up way over there on the right-hand side. And then furthermore, there's a standard formula for integrals like this that I'm overlining in red because I've got 1 over essentially x squared plus something squared, where that's a constant. So I can just write down the value of that. And that's in fact going to give us n to the 5th times pi over 2. I'll let you re-look up how to do that if you need to. Okay, so now what we can do is add the magenta side of the right-hand side to the left-hand side, or I guess I should say subtract. And that's going to give us 1 minus n to the 6th, and then the integral from 0 to infinity of x to the 6th over x squared plus n squared, and then x to the 6th plus 1 dx is equal to, well, let's observe that we can rewrite that as pi over 6 times, and here I'm doing a little work on its own. We can do a factorization of this. Maybe it's just, you would maybe find this just by kind of exploring. So this would be pi over 6 and then 1 minus n times n squared minus n plus 1 times 3n squared plus 4n plus 2. Okay, so we're left with something like this. And then furthermore, we can take this 1 over n to the 6th, which is way over here on the left-hand side of the equation, and I can factor that as 1 minus n times 1 plus n times, we've got n squared minus n plus 1, and then n squared plus n plus 1. So again, that's a semi-standard factorization for something of the form a to the 6th minus b to the 6th, a difference of 6th powers. But let's jump to that integral being solved for a nice rational function of n at the top of the board, and then we'll do our final calculation. Okay, so here's what we get when we solve for the integral that we wanted to, and then perform a pretty simple partial fraction decomposition. So we've got that integral is equal to pi over 6 times 1 over n plus 1 plus 2n plus 1 over n squared plus n plus 1. Okay, so now we've got that, we're ready for our final calculation. But before we move into the final calculation, thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing, it really helps out. Okay, so recall that we've got these 3 tools here, 2 from a previous video, 1 that we derived at the beginning, and then the 1 that didn't fit on the board, so we left it out. But we'll apply that pretty quickly. Okay, so the first thing that we're going to do is take this 1 over a hyperbolic sine and rewrite it like this. So that's going to split this integral up into 2 pieces. And let's also observe that it's going to take this x to the 5th in the numerator and bring it down to an x to the 4th in the first term. So just be aware of that. So this is going to give us the following. So we'll have a 1 over pi. That comes from the fact that we've got a hyperbolic sine of pi x here instead of just a hyperbolic sine of x. And then that's going to be all multiplied into the integral from 0 to infinity of x to the 4th over x to the 6th plus 1 dx. So that's again from this first bit. And for the second bit, we have plus 2, and then the sum as n goes from 1 up to infinity, and then we'll have minus 1 to the n, and then the integral from 0 to infinity of x to the 6th over, let's see, that's going to be x squared plus n squared times x to the 6th plus 1 dx. So again, that's just applying this rule right here. Notice that in this case, the x to the 5th in the numerator gets boosted up to an x to the 6th. But now we can apply some of the identities that we have come up with. So we've got a 1 over pi, and then this integral right here is simply pi over 3. We know that. And then here we're going to have a plus 2. The sum as n goes from 1 to infinity, minus 1 to the n. And then we're going to have a pi over 6. And then 1 over 1 plus n plus 2n plus 1 over n squared plus n plus 1. So that's from that other tool that we derived, or that other identity that we established. Okay, so now what I'm going to do is take this 1 over pi that's out front and have it cancel all of these pi's which are inside. So something like that. And then we're going to have this 2 cancel this 6 down to a 3. And then I'm also going to split this sum into 2 pieces. And so let's see what we get when all is said and done. So we're going to have a third, and then plus 1/3 times the sum as n goes from 1 to infinity of minus 1 to the n over n plus 1. So that's from this 1 over n plus 1 But now I'm going to do a trick. I'm going to start this at 0 instead of 1, but that means that I have added the number 1/3 to everything because that's the 0th term. That means I need to subtract a third to make everything work out. Okay, and then I'll have plus 4/3, and then the sum as n goes from 1 to infinity, n from 0 to infinity, of minus 1 to the n, 2n plus 1 over 2n plus 1 squared plus 3. And where did that 4 come from? Well, that came from multiplying this whole denominator by 4 so that we could perform this factorization that we have in the denominator here. Notice I can multiply by 4 over 4. I'll get a 4 in the numerator, 4n squared plus 4n plus 1 plus 3. Then the 4n squared plus 4n plus 1 factors as 2n plus 1 all squared. But then I changed that from starting at 1 to starting at 0, which means I added in a 1/3 term, which means I need to subtract off a 1/3 term. It's a 1/3 term here because it's a quarter term before multiplying by this 4/3. Okay, great. But now what I can do is, we'll take this third here, this minus third here cancel. And then let's observe that this is a standard series that we should maybe know. It is the natural log of 2. So we get 1/3 times the natural log of 2 minus a third from this third way over here. And then I'm going to write this in kind of a fancy way. This is going to be plus 4 pi squared over 3. And then we have the sum as n goes from 0 to infinity, minus 1 to the n, 2n plus 1, all over 2n plus 1 squared times pi squared times 4 times the square root of 3 over 2 all times pi squared. So I just multiplied by pi squared over pi squared, and then I did this goofy thing here where I took this 3 and I wrote it as this root 3 over 2 squared all times 4. Okay, nice. But why did I do that? Well, I wanted it to look like this formula right here, which has a 4 built in. So that means I can apply my formula for this hyperbolic secant, and in the end, I'll have this stuff that I'm just bringing down, this third natural log of 2 minus third, and then plus pi over 3, because I still have a 3 in the denominator. This doesn't have a 3 in the denominator. I still have a pi, because this simply has pi, not pi squared. And then I've got this hyperbolic secant evaluated at pi times the square root of 3 over 2. And that's the final value for our integral.